Something entered our solar system last year that, by the rules science has followed for decades, simply should not exist. And a fresh study out of China has now confirmed exactly why it's so unsettling. This is not a theory, this is not speculation, this is a measurement published in Nature in June 2026 that shows this object was born somewhere so frigid, so old, and so unlike anything in our own solar system that researchers are honestly struggling to fit it into the framework they've built their entire careers around. The water locked inside this comet carries 30 times more heavy hydrogen than anything ever recorded before. Its carbon signatures line up with nothing. Not our solar system, not the star-forming regions nearby, not anything on record. And when scientists reverse engineered those numbers to figure out when and where this object was born, the result came back at 10 to 12 billion years old. The universe itself is only 13.8 billion years old. This thing has been drifting through interstellar space for longer than our sun has even existed, and it just swept through our cosmic neighborhood. Let that sink in. This is the story of 3IATLAS. What it is, what Chinese researchers uncovered that nearly the entire world overlooked, what the newest findings tell us about its origins, and what it all means for everything we believed we understood about the cosmos and our place inside it. July 1st, 2025. The ATLAS Survey Telescope in Rio Hurtado, Chile, picks up a faint object drifting across its nightly scan. Automated systems flag it the way they flag thousands of objects every month, but this one stands apart. The orbit calculation comes back strange. It's rerun. Same result. This isn't a glitch. The object's eccentricity, a measure of how stretched its orbit is, comes out to 6.14. An eccentricity of exactly 1.0 marks the line between an object that stays bound to the sun and one that's simply passing through, never to return. A reading of 6.14 isn't a comet drifting in from our solar system's outer rim. It isn't a long-period comet swinging back after a million-year loop. It's a body moving so fast, on a path so extreme, that it could only have originated somewhere entirely outside our solar system, from another star altogether. Astronomers quickly named it 3IATLAS, the third interstellar object ever confirmed. The first was 1I Oumuamua in 2017, a bizarre, elongated body that sailed through with no tail, none of the outgassing you'd expect from a comet, leaving scientists baffled before it vanished into darkness again. The second was 2I Borisov in 2019, a more familiar interstellar comet that at least behaved the way comets are supposed to. 3IATLAS broke the mold from both of them instantly. Its eccentricity dwarfed either predecessor. Its speed relative to the sun, what's called its hyperbolic excess velocity, clocked in around 58 kilometers per second. That figure matters because it isn't just a speed reading. It's essentially a clock. The faster an interstellar visitor is moving when it crosses into our solar system, the longer it's likely been wandering through interstellar space since whatever event first flung it out of its home system. And 58 kilometers per second is extremely fast. Fast enough that when University of Michigan researchers ran the numbers, they landed on a formation age somewhere between 3 and 11 billion years. Newer isotope readings from James Webb have since pushed that figure higher still, toward 10 to 12 billion years. Our own sun, for comparison, is 4.6 billion years old. This object predates the star we're orbiting right now. But before diving into the chemistry that revealed all of this, we need to talk about what unfolded in September 2025, a 36-hour stretch when most of the planet's premier telescopes went dark at precisely the wrong moment, and what China quietly did during that gap that hasn't gotten nearly enough attention. 3IATLAS was moving fast, faster than any comet we'd ever tracked this closely before. So any break in observation wasn't just an inconvenience. It meant irreplaceable data lost for good. In late September 2025, as the comet neared its closest approach to the sun, several of the world's most powerful observatories happened to go offline. At the same time, Hubble was undergoing gyroscope recalibration to hold its pointing steady to within a tenth of an arcsecond. James Webb was mid-swap between instruments, a thermal stabilization process that eats up more than a day. The Very Large Telescope in Chile was in the middle of cleaning its primary mirror using jets of carbon dioxide snow to lift off microscopic dust. Gemini North in Hawaii and Gemini South in Chile had both already been redirected to other pre-scheduled programs, locked in months ahead through competitive international time allocations that aren't easy to override on short notice. The upshot? A 36-hour window, with no major Western optical or infrared telescope watching 3IATLAS. In that span, the comet covered more than 1.2 million kilometers along its path. With no continuous eyes on it, the brightness curve, the record of how its light output was shifting as solar heat intensified, had a blank spot right when peak activity was expected. That's not a small gap. It undermines the very model scientists used to describe how the comet's ices were behaving, how quickly material was escaping, what its spin rate looked like, how dust and gas were balanced at maximum heating. This was a genuine hole in the observational record of the strangest visitor to pass through our solar system in living memory. What closed that hole was China. High-altitude observatories in Tibet, Qinghai, and Yunnan don't run on the same maintenance schedules as their Western counterparts. Their daylight cycles, their instrument calendars, none of it lined up with the simultaneous downtime hitting Hubble, the VLT, and the Gemini network. Ali Observatory in Tibet, the Qinghai Station near Dalinga, and Yunnan Astronomical Observatory all stayed active straight through the entire 36-hour gap, operating at altitudes where thin, dry air cuts down dramatically on atmospheric distortion. These sites kept their instruments locked onto 3IATLAS, logging its position, brightness, and the evolving shape of its coma without a single break. Every observation was time-stamped to the millisecond using GPS-synced clocks. Every image was archived in standard FITS format with complete metadata. The files were sent to the National Astronomical Data Center in Beijing, screened for corruption, run through calibration, and posted to the China VO Sky Survey portal within 12 hours of being captured. There was no press release, no promotional push. It was just a routine data update. But to any astronomer who understood what had just been missed elsewhere, those files were the single most valuable data set from that entire stretch. Once Hubble came back online, once Webb finished switching instruments, once the VLT's mirror was clean again, every research team's first move was pulling the Chinese archive to recalibrate their own numbers. The positional uncertainty for 3IATLAS fell from roughly plus or minus 25 arc seconds down to under 5. The missing brightness curve got filled in, the outgassing timeline was recovered. The peak activity window, which had been on track to go permanently uncharted, now had unbroken coverage. A 36-hour data handoff from 3 mountain observatories in Asia quietly became the backbone of every scientific analysis that followed. No fanfare, no headlines, just data uploaded, used, and absolutely essential. This piece of the 3IATLAS story says something real about how global science actually functions. The world's biggest telescopes cluster in a handful of locations, mostly in the Americas, mostly run by Western institutions, mostly booked through annual proposal cycles that lock in observing time months in advance and can easily bend for the unexpected. China's observatory network is built differently. Several mid-sized instruments running in parallel, automated scheduling that can pivot toward breaking. Events and a geographic footprint that opens up night windows Hawaii and Chile simply don't have. For a fast-moving target that demanded nonstop coverage, that distributed setup proved more valuable in a crisis than any single giant mirror could have been. Now here's where things get genuinely hard to wrap your head around. Because what all these telescopes, Chinese, American, European, Japanese, collectively measured about 3IATLAS isn't just odd. It's the kind of result that sends researchers back to re-examine assumptions treated as bedrock for decades. James Webb captured 3IATLAS in December 2025 as it moved away from the Sun following its closest approach in late October. The comet's ancient ices, freshly exposed to solar heat, were vaporizing into a bright coma of released gas, perfect conditions for spectroscopic study. Webb locked onto it and recorded the chemical signature of what was streaming off the nucleus with a precision no earlier instrument could match. Those findings were published in Nature on June 22nd, 2026. The first thing that stood out was the water, and not ordinary water. 3IATLAS is loaded with unusually heavy water. Heavy water forms when one or both hydrogen atoms in a water molecule are replaced by deuterium, a hydrogen variant carrying an extra neutron. Deuterium exists throughout our solar system. Trace amounts show up in Earth's oceans. Small but measurable amounts turn up in solar system comets. The ratio of deuterium to ordinary hydrogen in our solar system's water, across comets, across Earth's oceans, across nearly every body we've studied, follows a consistent pattern tied to the conditions our solar system formed under 4.6 billion years ago. 3IATLAS shattered that pattern entirely. The deuterium to hydrogen ratio in its water measures roughly 30 times higher than typical solar system comets and more than 40 times higher than Earth's oceans. That's not a small deviation. That's not a reading that drifts slightly outside the norm. That's a chemical composition scientists have never encountered in anything from our own solar system, and one that doesn't match any nearby star-forming region we've measured with modern equipment either. Martin Cordner of NASA's Goddard Space Flight Center, who led one of the key spectroscopic studies, put it plainly, what they're looking at is an object that doesn't match our solar system, doesn't match our own comets, and doesn't match nearby protostars either. This is something new, something different. Building up that much deuterium in water ice takes two specific ingredients. First, extreme cold during formation. The chemistry that favors deuterium enrichment works best near absolute zero, far colder than the warm inner disk where planets take shape. Second, enormous stretches of time. Deuterium enrichment doesn't happen fast. It builds up gradually under conditions of deep cold and dense molecular cloud chemistry. Put together, these point toward a birthplace in the outer reaches of a very young galaxy, back when molecular clouds ran denser and colder than they do today, when the universe held far fewer heavy elements, when stars were forming under conditions that simply don't exist in our part of the galaxy anymore. Webb's carbon isotope readings backed up the same conclusion. The chemical fingerprints in 3IATLAS place its origin somewhere between 10 and 12 billion years ago, in a region of the galaxy far colder and far more primitive than the cloud that eventually gave rise to our sun. That's what China's study confirmed and built upon. The uninterrupted data from Chinese observatories during the September blackout supplied the unbroken brightness curve and positioning that let Webb and the other instruments confidently pinpoint exactly what they were observing during each stage of the comet's solar approach. The chemical analysis that dated 3IATLAS at more than double the age of Earth couldn't have been carried out with the same confidence without that gap-filling data. The complete picture only exists because two separate global astronomy systems were running side by side, and the one that drew the least attention ended up being the foundation for the result that matters most. Let's sit with what this object actually represents for a second, because these numbers stop feeling real if you skim past them too fast. 3IATLAS formed roughly 10 to 12 billion years ago. At that point, the universe was under 4 billion years old. The earliest generations of stars had already lived and died, scattering heavier elements through the galaxy for the first time. Our sun didn't exist yet. The cloud of gas that would eventually collapse into our sun, our planets, and every living thing on Earth hadn't even come together. 3IATLAS was already drifting through interstellar space when all of that was still ahead of it, likely flung out of its home star system by the gravitational pull of a large planet passing too close. And then it just kept traveling for billions upon billions of years through the emptiness between stars, through the spiral arms of the Milky Way, through the frozen interstellar medium where almost nothing happens beyond the slow migration of ancient matter through ancient space. It was already unfathomably old by the time Earth formed. It had already been journeying longer than our entire solar system has existed before the first single-celled organism ever appeared in Earth's oceans. And then, after all that time, on a trajectory locked in by a gravitational encounter more than 10 billion years in the past, it happened to swing close enough to our sun to briefly show up in our sky. Spotted by a telescope in Chile on a Tuesday morning in July 2025, and then studied intensely by nearly every major observatory humanity has ever built. The carbon dioxide to water ratio added yet another layer of strangeness. In typical solar system comets, water dominates and CO2 shows up as a minor player. In 3IATLAS, the CO2 to water ratio measured 7.6. In solar system comets, that figure usually sits around 0.12. 3IATLAS carried over 60 times more CO2 relative to water than the comets we're familiar with. That tells researchers the ices in this object either formed much closer to the CO2 frost line of its home star system, far colder territory than where water ice condenses, or that billions of years of galactic cosmic ray exposure heavily reworked those ices during its interstellar journey, possibly both. The carbon monoxide to water ratio told a similarly extreme story, coming in near 1.65 against a typical solar system median of about 0.3. This is the unfinished monument of the interstellar unknown, and it's also the unfinished monument of our own understanding. We pointed Hubble, Webb, Spherex, ALMA, Gemini, the VLT, and more at this object, and everything they return tells one coherent, unmistakable story. 3IATLAS is genuinely, measurably, chemically unlike anything native to our solar system. It didn't come from nearby. It didn't come from a star resembling our sun. It came from an environment that existed early in the galaxy's history, under conditions that no longer occur anywhere near us. And it has been carrying that chemical signature, frozen into its ice, for a stretch of time longer than our sun has been shining. There's also the matter of what 3IATLAS did near Mars. Its path carried it within 0.194 astronomical units of Mars on October 3rd, 2025. Not a collision, not even a particularly close pass-by. Interstellar standards, but near enough that ESA's ExoMars Trace Gas Orbiter and a second European spacecraft in Mars orbit both turned their instruments toward it, capturing images of its full coma structure from an angle no ground-based telescope on Earth could match. Those images revealed extended dust streamers and intricate outflow patterns, consistent with vigorous, active sublimation happening across multiple regions of the nucleus's surface, Whatever this object held inside was escaping rapidly as the sun's heat intensified. So what does all of this actually confirm? And what did people fear? Not a threat. The comet never came within 170 million miles of Earth. There was no danger to anyone. What it confirms instead is something more philosophically weighty, and in some ways tougher to sit with than any threat would have been. It confirms that the interstellar medium, the space between stars, isn't empty, it's occupied. Occupied by debris shed from star systems that formed billions of years ago and burned out long since. These wandering objects aren't just rocks drifting through the dark. They're archives, physical records of conditions that no longer exist anywhere within our reach to directly observe. When 3IATLAS released its ancient ices under the heat of our sun, feeding the coma that Webb was able to study, it was letting loose material that had stayed frozen since before Earth ever formed. Material assembled under conditions that current models of the early galaxy predict, but had never actually been measured directly until now. In a very real sense, we didn't just observe a comet, we sampled the early universe, and China's observatories made certain we didn't lose 36 hours of that sample during the single most critical window for observing it. That's the practical reality sitting beneath the dramatic headlines. And the broader question this all raises about global astronomy isn't a comfortable one, but it deserves to be said plainly. The story of the September blackout, and China's role in covering it, exposes a real structural weakness in how humanity keeps watch over the sky. The largest, most capable instruments sit concentrated in a small handful of places, booked out months ahead through funding systems that don't flex well for genuine surprises. And when they all go dark at once, even briefly, there's no ready Western backup. The assumption that the biggest telescopes will always be available is exactly the assumption that fails you the moment you need it most. What China proved is that a distributed network of mid-sized instruments built for duty cycle rather than raw power, automated for quick repositioning, spread across different night windows, can deliver something the concentrated giants can't: uninterrupted continuity. For a fast-moving, once-in-a-generation target like 3IATLAS, that continuity turned out to matter more than any single observation from the most powerful telescope on the planet. The last thing worth holding on to is what researchers said when the Nature paper landed in June 2026. The isotopic fingerprint of 3IATLAS isn't merely unusual, it's unlike anything ever measured in our solar system or anywhere close to it. This object arrived from somewhere our instruments have never reached, from a time our telescopes can't access directly, and it hauled its chemistry across more than 10 billion years of interstellar travel, just to release it, briefly and brilliantly, into the glowing coma that formed as it swung past our sun. Researchers working backward from that chemistry, trying to pin down what kind of molecular cloud, what kind of early galaxy environment, what conditions could possibly produce such extreme deuterium ratios and such exotic carbon signatures, are still at it. No existing model lines up perfectly with the data. This object matches nothing in our current catalog of measured environments. And that's the real takeaway from the new study. Not simply that 3IATLAS is old, not simply that it's foreign, but that it is genuinely, measurably beyond the boundaries of everything we've used as a reference point until now. The universe is older and stranger than our models accounted for. The interstellar medium holds objects formed under conditions we've only theorized about. And our solar system isn't a sealed garden, it's a waypoint. Things pass through it that were born before Earth existed, before the sun existed, shaped by an early universe whose conditions no longer exist anywhere close enough for us to study firsthand. Except, that is, when one of them drifts through our sky. Except when a survey telescope in Chile catches a moving speck and the numbers come back too extreme to belong to anything local. Except when humanity's instruments, from Hawaii to Tibet to Mars orbit, all turn together towards something that, by the rules science followed just a decade ago, shouldn't be here at all. 3IATLAS is already gone, past Jupiter's orbit now, heading out of the solar system on a path that will never bring it back. The ice it still carries will refreeze in the dark of interstellar space. The coma will collapse, the tail will fade, and it will keep drifting for another 10 billion years or more, hauling its ancient chemistry toward whatever waits for it further out in the galaxy. But the data it left behind is preserved now, in the journals, in the archives, in the spectrographs, in the isotope ratios captured by James Webb and ALMA, anchored by the uninterrupted brightness measurements taken through a 36-hour blackout by observatories on Chinese mountaintops that almost nobody had heard of before July 2025. The universe sent us a message frozen inside 10 billion-year-old ice. We nearly missed part of it. We didn't. Drop your thoughts in the comments. What does it mean that the oldest object ever observed in our solar system came from conditions no existing model can fully explain? Subscribe, because the next video picks up exactly where 3IATLAS went after Mars, and what the data reveals once its full trajectory is mapped against the history of the galaxy. Something reached us from the early universe. We studied it, and what it revealed confirms that the cosmos is far older, far stranger, and far more crowded with ancient wandering debris than anything we ever feared or hoped.